My name is Birza Mariam from the Department of BS Biotechnology, and the topic of my presentation is electron paramagnetic resonance. It is a technique which uses the spinning property of an electron, which are in resonance, or you can say that electron spin resonance or electron paramagnetic resonance, based on the paramagnetic behavior of an electron, which are in resonance. Let's understand how the spinning property of an electron or how the paramagnetic property of an electron help in resonance, which used in spectroscopy. Suppose that it is a molecule and a molecule consists of atom. An atom consists of nucleus. In nucleus, there are positive charge proton and neutron. So the overall charge of nucleus is due to proton and charge around the nucleus. Negative charge around the nucleus are due to the electrons are present. Electrons has the property to rotate around its own axis. When a charged body rotates, it behaves like a magnet. Electrons has negative charge and revolve around the nucleus. So here electrons behave like a magnet and generate magnetic field. Let's understand how the magnetic property of the electron is used in the working of the ESR or EPR. Suppose it is an electron. An electron is revolving around its own axis, so it behaves like a magnet. One property is paramagnetic and the other is diamagnetic. Let's understand diamagnetic and paramagnetic behavior of the rotating electron. Diamagnetic behavior is shown by molecules which have paired electrons. Suppose a molecule contains two electrons. If an electron is rotated in a clockwise direction, then its magnetic field is directed by an arrow pointing up. And if an electron is rotating in an anticlockwise direction, then its magnetic field is directed by an arrow pointing down. Due to the antiparallel magnetic field, the magnetic field generated by each electron cancel each other magnetic field. So you can say that there is the self-cancellation of magnetic field by the electrons which have opposite spins. Next come to paramagnetic behavior. Paramagnetic behavior is shown by molecules which have unpaired or odd number of electrons. Suppose a molecule contains a single electron. This electron may rotate in clockwise or anti-clockwise direction. There is no other magnetic field, so there is no self-cancellation. In ESR or EPR only, paramagnetic behavior is used because in ESR only unpaired electrons are attracted. Example, ferrous, cobalt, nickel. Free radicals and electrons of triplet state show paramagnetic behavior. To explain this, we use a special term called spin quantum number represented by symbol ms. Ms has two values, plus 1 by 2 and minus 1 by 2. If the electrons are paramagnetic, then it has only plus 1 by 2 or other minus 1 by 2 value. And if they are diamagnetic, then will show both plus 1 by 2 and minus 1 by 2 to show opposite spin of both electrons. Next come to the technique of ESR or EPR. Suppose that it is an ESR chamber and this ESR chamber contains a magnet. We create an external magnetic field or applied magnetic field by using this magnet. The magnetic field created by using this magnet is called applied magnetic field and it is of 50 to 500 millitesla or in Gauss it is of 3400 Gauss. In next step, we put a molecule which contains an unpaired electron and it is rotating in an anticlockwise direction. We don't know what is the orientation of an electron. When we create an applied magnetic field, the direction of an applied magnetic field in parallel direction and this electron is rotating. So it is also behave like a magnet and generate magnetic field. This applied magnetic field causes the alignment of the spinning electron. So after alignment, this spinning electron align in the Direction of applied magnetic field. Such condition in which direction of both the magnetic field and are same, such condition is known as alpha state. Alpha state is always a parallel state and alpha state is always a lower energy state. In next step, we provide some energy to the electron in alpha state. Energy in the form of radiation and radiations provided in the ESR machine are microwaves. These microwaves are generated from klystron oscillator or of 3 cm wavelength or 9 GHz. This microwave radiation, when incident on an electron, then this electron opposes the direction of applied magnetic field and it changes its direction and shifts its position. And after shifting its position, it is just an opposite direction to the applied magnetic field. The direction of magnetic field created by ESR machine is in downward direction and the direction of magnetic field created by an electron is in upward direction and hence both the direct magnetic field are in opposite direction and such condition is known as beta state. And beta state is always an antiparallel state and high energy state. As you can observe that electrons are present in alpha state and after absorbing microwaves, it shifts its position to the beta state. The changing in the direction of the spinning electron is known as resonance. As this resonance is shown by an electron is spinning, so it is known as electron spin resonance. And the technique used to study the electron spin resonance is known as electron spin resonance spectroscopy. Now, what happened if we block microwave radiations or what happened if we block the energy source? If we block the microwave radiation, then electrons which present in beta state return to the alpha state. It shifts its position and the direction of applied magnetic field and direction of spinning magnetic field are in same direction. All the above procedure in which electrons change its state from alpha to beta and beta to alpha is known as resonance, which are present in spin. So it is known as electron spin resonance. Now, the question arises why the paramagnetic behavior is used in the working of ESR. The answer of that question is that only the paramagnetic electrons are attracted in applied magnetic field. That's why we use the electrons with odd number. Now, here are some general information about EPR, which is electron paramagnetic resonance. Here are the properties of the compound we use in electron paramagnetic resonance technique. The compound used must be inorganic and always present in solid form. If it is present in liquid form, like liquid nitrogen, we convert it into crystal form and then use the compound. And the compound must have unpaired or odd number of electrons. Here are the applications of EPR. Electron paramagnetic resonance or electron spin resonance spectroscopy is used in various branches of science, such as biology, chemistry, and physics, for the detection and identification of free radicals and paramagnetic centers, such as F centers. Electron paramagnetic resonance is a sensitive, specific method for studying both radicals and formed in chemical reaction and the reactions themselves. For example, when ice, solid H2O is decomposed by exposure to high energy radiations, radicals such as hydrogen hydroxide and H2O are produced. Such radicals can be identified and studied by electron paramagnetic resonance. Organic and inorganic radicals can be detected in the electrochemical system and materials exposed to UV light. In many cases, the reactions to make the radicals and subsequent reactions of the radicals are of interest, while in other cases, electron paramagnetic resonance is used to provide the information on our radical geometry and the orbitals of the unpaired electron. Paramagnetic resonance or spin resonance spectroscopy is also used in geology and archaeology as a rating tool. It can be applied to a wide range of materials such as carbonates, sulfates, phosphates, silica, or other silicates. Electron paramagnetic resonance has proven itself as a useful tool in homogeneous catalysis, research for characterization of paramagnetic complexes and reactive intermediates. Electron paramagnetic resonance spectroscopy is a particularly useful tool to investigate their electronic structures, which is fundamental to understand their activity. Medical and biological applications of electron paramagnetic resonance also exist. Although radicals are very reactive and do not normally occur in high concentration in biology, special agents have been developed to spin label molecules of interest. These reagents are particularly useful in biological systems, especially especially the specially designed non-reactive radical molecules can attach to the specific sites in biological cell and electron paramagnetic resonance spectra can then give information on the environment of these so-called spin labels or spin probes. Spin labeled fatty acids have been extensively used to study dynamic organizations of lipids protein interactions in biological membranes. Lipid protein interaction and temperature of transition of gel to lipid crystalline phases. Electron paramagnetic resonance or electron spin resonance spectroscopy can be applied only to systems in which the balance between radical decay and radical formation keeps the free radical constriction above the detection limit of the spectrometer. This can be a particularly severe problem in studying reaction in liquids, and alternative approach is to slow down reaction by studying samples held at cryogenic temperatures such as 77 K liquid nitrogen or 4.2 Kelvin liquid helium. An example of this work is the study of radical reaction in single crystals of amino acids exposed to X-rays. We work that sometimes leads to activation energies and rate constants for radical reaction. The study of radiation induced free radical in biological substances for cancer research possesses the additional problem that each tissue contains water due to its electric dipole moment has strong absorption band in the microwave region used in the electron paramagnetic resonance spectrometers. Electron paramagnetic resonance or electron spin resonance is also used archaeologists for the dating of teeth. Radiation damage over a long period of time creates free radical in tooth enamel, which can then be examined by EPR and after proper calibration, dated alternatively material extracted from the teeth of people during dental procedure can be used to quantify their cumulative exposure to ionizing radiation. People exposed to radiation from Chernobyl disaster have been examined by this method. Next is radiation sterilized foods have been examined with PPR spectroscopy, the aim being to develop methods to determine whether a particular food sample has been irradiated and to what dose. Electron paramagnetic resonance or electron spin resonance spectroscopy has been used to measure properties of crude oil, in particular aspartame and vanillus content. Electron paramagnetic resonance measurement of aspartame content is a function of spin density and solvent property polarity. In the field of quantum computing, Pulsed electron paramagnetic resonance is used to control the state of electron spin pivots in materials such as diamond, silicon, and gallium arsenide. That's all for this video. Thank you.